Everybody, today I have a problem that I think is rather fascinating, and I'll tell you why. Math has a reputation for being kind of dry, and you do it this way, and that's the way it's done. But this math is a kind of a venue for multiple interpretations, and this problem is an example of that. I'm trying to show you that n factorial divided by 2 to the m is always a natural number. That means it's a fraction. It's not a fraction, okay? It's a number like 1, 2, 3, positive integer, okay? Now, the connection here between n and m is that n is flat out equal to 2m. So n is an even number. We want to show that n factorial divided by 2 raised to the m power is a natural number. Now, it's not too surprising. Those of you familiar with factorial, there's plenty of 2's to go around, but we'll still prove it. Okay. Now, we're going to proceed combinatorically, y'all, and this just means combinatorics is the mathematics of counting the number of states some kind of system is in. Okay, and this is kind of a famous example. Find the number of permutations of the letters in Mississippi. Permutations is just an order arrangement of the symbols. Now, if you'll notice here, there's 11 letters in the word Mississippi. All right, and so the way you do this, a lot of you, I'm sure, have seen this. There are 11 letters here. They're not all distinct, of course. Again, a very famous problem that appears in a lot of algebra books when they're talking about permutations and combinations and discrete math books, but 11 factorial, okay? 11 factorial. Okay, now the way you count the number of permutations, if all 11 of these letters were distinct, 11 factorial would be the number of permutations, right? But notice that we have 1, 2, 3, 4 occurrences of the indistinguishable symbol S. And so we divide by 4 factorial to kind of shave off the order there that would exist if the 4 S's were distinct symbols. Okay? So there's 4 S's, right? There's 4 S's. Oh gosh, there's also 4 I's, right? 1, 2, 3, 4 I's. So we have 4 factorial again, right? And then what else do we have? 2 P's, right? 2 P's? 2 P's, all right? So we have divided by 2 factorial. Okay, y'all, I'm laboring on the assumption that we have 2 P's. Okay, that's the 2 factorial. Because you could think of this is P sub 1 and P sub 2, there would be 2 factorial ways to arrange those 2 P's, but since they're not, they are indistinguishable, we divide that out. Okay, it's a combinatorics idea, all right? And then I'm counting everything else. There's 1 M, right? And then there's, what else? There's 4 S's and 4 I's, right? Okay, so this is the number. So notice, now I'm not going to calculate this because I don't feel like doing it right now, but this is some integer, okay? This is a member of n. And I'm just being lazy because I don't want to go to the trouble to calculate that. But it wouldn't be so hard to do. You could whop off the 4 factorial and go through and do it. But anyway, just trust me, you can calculate that if you want. It is a natural number, okay? So this is always the case. The number of permutations of the letters has to be a natural number, otherwise this formula is completely bankrupt, right? So we're laboring under this assumption that this counting technique is always going to yield an integer. Now, I'm not proving it for you. That you could look at the proof of that in a discrete math course, okay? So here we go. Let's use this idea. Okay, now n is equal to 2m, and if we interpret the 2m in this way, we have a couple of y sub 1's, a couple of y sub 2's, a couple of y sub 3's, all the way to a couple of y sub m's, right? So we have 2 indistinguishable symbols, and there's 2m of them just by construction here, right? So we get n is equal to 2m, right? So we can write down n factorial, right? And then in the same sort of way that we did before, it's just 2's are our number here. So we can write down 2 factorial m times, right? There's m occurrences of these 2 symbols, right? Combined. So I'm going to do 2 factorial, 2 factorial, and let's go ahead and put the ellipsis. And we'll close with 2 factorial. And the nice thing about having something to write with rather than an equation editor is I can write m times right under this. M times. Okay, this happens m times, but you see this is equal to If 2 factorial is just trivially 2, right? So this would be equal to the n factorial over 2 to the m. Wham. Okay. And remember, that is what we were trying to show. Okay, show that n factorial over 2 to the m is a integer, a natural number. And again, I was a little light here. I didn't prove to you why this is true, but if you believe this, that this does count the number of permutations of a group of symbols where there's a lot of repetition, then the result follows. This is a natural number. Okay? Y'all, I liked it. Okay, combinatorics problem. And again, we just interpreted this problem in a way that was a little weird. I saw this in a Grimaldi discrete mathematics book. Okay? Good night.